Yeah, sure. Yeah, we actually lost some classes, but we will actually try to make it up. But still, we are actually ahead of other sections. So let's see. If needed, we will actually have some uh, extra classes later. Okay. I don't think that will be needed because we are already ahead of other sessions. So yeah, that is actually fine. Yeah. So in the last class, we were actually in the last class we were having the tutorial session where we actually saw some problems from uh, heat with heat generation, 1D heat with the heat generation, as well as for cylindrical system with the heat generation. Okay. So I know the fins, the heat transfer problems on fins are actually pending. So we'll actually try to cover that this week itself. Okay. I will actually send you the problems for the next tutorial by this weekend, this today itself, so we can actually go through that. So in the last class, we started with the transient heat transfer mechanism, right? So transient means we said that there is actually change in the temperature with the time. So till now, for the one-day slab or steady state condition, we actually assume that the heat or the whatever the temperature profile within the surface is actually constant. It was actually not varying with the time, whether it is actually with heat generation or without heat generation. It was in a steady state condition. It was not varying with the time. But in many of the practical situations, what we are actually having is actually the surfaces or bodies in which the temperature is actually varying with the time. Okay? Such situation is actually known as the transient heat conduction. Okay. So real body. So therefore, we can see that temperature it is actually going to be a function of all the coordinates and time. If you're actually talking about a 1D conduction, then it is actually going to be a function of only of the direction in which temperature is actually vary. In our particular case, it will be x and time t. Okay. So whatever the calculations or whatever the derivations we are actually going to do are actually for the the Cartesian system. Okay. But we can actually extend whatever we are actually doing to the other systems like the cylindrical as well as the spherical systems also. Okay, because the derivations it's actually going to be a bit involved, so it is easy for us to understand from a Cartesian point of view or Cartesian system point of view, but we can actually extend it to the other systems also. Okay, and we said that there are actually three physical problems in which or the three types of problems we can actually encounter in the uh, transient system. First one is actually the lumped capacitance method. Second is actually the semi-infinite method, and third one is actually the finite solid method. And also we said we will actually be considering all the analysis without heat generation. With heat generation, again, it's actually going to be a bit involved. But once you actually understand the mechanism or whatever the heat transfer, whatever is actually happening without heat generation, we can actually always be extended to the with heat generation condition. So then we said we started seeing or we actually saw fully the empty capacitance method. In this case, we actually said that we are actually neglecting the temperature gradient within the solid surface. Okay, so therefore we can actually say that we are actually assuming the full body of at the same temperature, but the temperature is actually varying with the time. It is not a function of any coordinate, only the function of temperature time. So we said first what is actually the criteria for doing that. For that, we actually did the energy balance at the surface, and we actually said that the temperature within the surface, okay, within the surface T1 minus T2 temperature gradient within the surface can be actually ignored compared to temperature difference between the surface and the ambient. So the temperature gradient within the body is actually ignored compared to the temperature difference between the body and the ambient. If there is actually one number known as a Biot number, it is actually much less than 1, where Biot number is HL by K. So therefore, we can actually see that if the heat transfer or the conduction resistance within is actually going to be much less than that of the convection resistance. Okay, so conduction resistance within means the heat is actually transferred within the body very easily, even with a very small temperature differences. The temperature is actually going to be or the heat is actually going to be there. Okay. So, yeah. So that term, the ratio of conduction resistance to convection resistance, which can be actually written as HL by K, is actually the Biot number. And we said that if the Biot number is actually going to be very less than much less than 1, then we can actually assume the temperature within the surface is actually constant compared to the temperature difference between the body and the surrounding fluid. Yeah. So the criteria for using this linked capacitance is actually therefore Biot number less than 1, much less than 1. Practically, we are actually taking Biot number if it is less than zero point 0.1, less than or equal to zero point 0.1, we can actually use that. Okay. So this is actually not a derived hardcore criteria or something. If it is less than zero point 0.1, we are actually getting a decent accuracy. If you want a very much accurate, then you can actually say I'm going to use it only if Biot number is actually less than 0.01. Okay. Or we are actually saying I don't want any accuracy at all, I just want a rough calculation, then you can actually say okay, Biot number less than 1 itself I am actually going to take. Okay. But usually Biot number less than zero point 0.1 we can actually assume it to be, we can actually assume to take it as the lambda capacitors. Okay. So then we actually saw the analysis itself. We said that initially we are having a body with the temperature Ti. That means initial temperature at T is equal to 0. It is having a temperature T is equal to Ti. At time T is equal to 0 itself, it actually put it into the water or any liquid. Liquid is actually at a temperature T infinity. So therefore, obviously, if the in our analysis we are actually assuming uh, yeah, T infinity less than Ti. That means initial temperature was actually high. So therefore, we know that the body is actually going to do some heat to the surrounding fluid. Since we are actually not dealing with the heat conduction within, we cannot actually use any of the heat diffusion equations and all. Okay? Because minus k dt by dx is actually not valid because dt by dx is actually going to be 0 over here. So we have to actually go for the basic energy balance. So with the energy balance over a small interval dt, we actually said that heat transferred from the body is equal to the decrease in energy of the body because since there is actually no heat generation, so whatever the heat or whatever the energy associated with the body, that is actually given to the surrounding fluid. Okay. So with that, the heat transfer from the body, we have actually wrote as H A surface into T minus T infinity into dt because we are measuring it for the time dt is equal to mcp dt. Okay. Yeah. So we actually rearrange it, and therefore we actually got the relation such that d theta by dt is equal to dt by dt. Okay. Yeah, we actually got the relation. Yeah, we actually put theta is equal to t minus t infinity. So therefore, we are actually getting the relation d theta by dt is equal to dt by dt. So we are actually putting into our basic equation. We are actually going to get HAS theta is equal to rho Vc d theta by dt. Okay. So we actually rearranged it and we actually integrated, and we actually got the final equation, okay, which is actually written as theta by theta I, where theta is equal to t minus t infinity. Theta I is equal to Ti minus t infinity. Okay. So therefore, we can actually see that theta I, that is actually the maximum change in the temperature that can actually have. Okay. Yeah. Yeah. So theta I, yeah. So that is actually given us uh, exponential of minus HAS by rho Vc into T. And we said that this term HAS by rho Vc, it is having the unit or rho Vc by HAS, rho Vc by HAS, it is actually having the unit S, and therefore we are actually calling it as the time constant. Okay. So therefore, we are actually writing it as t minus t infinity divided by ti minus t infinity is equal to e raised to minus t by tau. Okay. Yeah. So we actually know that at time t is equal to 0, t minus t infinity divided by ti minus t infinity, it will be actually going to be equal to 1, right? It will be actually 1. Because at time t is equal to 0, temperature of the surface is actually Ti. Okay, so therefore that is actually going to be equal to 1. At the time tends to infinity, we know that t is actually tending to t infinity. Okay, so therefore it is actually theta by theta I, it is actually tending to 0. Okay. And we said that again at time t is equal to tau, at time t is equal to tau, we said that the time step or the temperature change, total temperature change, is equal to 63% as that of the total step change. Okay, the total change in the temperature of the body means Ti minus T. That is actually the change in the temperature of the body, right? Change in the temperature of the body is 63% of the step change. Okay, step change means it is actually the maximum change, or that is actually the sudden change in the boundary condition. Okay. So that is actually the importance of tau. So therefore, we can actually see that as we are actually reducing the tau, we are actually going to reach the 63% of the step change very fast. Okay. Yeah. And then again, we actually wrote again these terms in terms of Fourier number as well as the Biot number. Where Fourier number we can actually write as alpha t by L LC, where LC is actually the characteristics length. Okay. And Biot number, it is actually HLC divided by KC. HLC is actually the characteristic length. Okay. So alpha t by LC, it is actually the Fourier number, which is actually the non-dimensionalized number. So we will see more of this Fourier number when we are actually talking about a semi-infinite method. So by the elliptic capacitance, we can actually write a theta by theta I is equal to e raised to minus b Biot number into Fourier number. And again, another important term, what we actually saw was actually the total heat transfer occurring up to any time t, okay, from initial time to up to any time t. So that we actually said that that we have to actually simply integrate over time. Okay, so Q is actually the heat flux at any time. Q is heat flux at any time, or thought heat transfer at any time. Heat transfer at any time. Okay, at any time we can actually write as which is equal to H into As into T minus T infinity. T is actually the temperature at any time, and T infinity is actually the outside ambient temperature. So T minus T infinity is actually the temperature potential at any particular time. So that is equal to theta. Okay. So therefore we have to actually integrate it over time, and then we are actually going to get the expression. So that also we can actually write as Q transfer. That is actually one method. Okay, so that is actually one method for doing this. Second method is that we are actually seeing how much is actually the change in heat transfer. Okay, yeah. So how much is actually the change in total energy of the system? So in that case, we can see that it is rho Vc into T minus Ti. So it is actually going to be rho Vc T minus Ti. Again, this term, if you actually see, T is actually going to be there, but we are actually not, we don't know what is actually T. So in order to find T, again, we need to actually use the term theta by theta I is equal to e raised to minus T by 2. Okay. So based on that only, you can actually find what is actually this T. Okay. So if you are actually doing that, then again, you will actually come up with this particular term. Okay. So basically both equations you will actually get same, only that it is actually both are written or both are actually derived from a different point of view. Okay. Yeah. So this is where we actually stopped in the last class. Any doubts still here? Because this is actually a simple concept. Okay. So any doubts you ask, it doesn't matter how silly that question is. If you have any doubts at all, we can actually discuss. All clear?
Yes, sir.
Okay, so if it is all clear, then we can actually move to the uh, next method, which is actually the semi-infinite solid method. Okay. So we actually saw the length capacitance. We actually said that there are actually three methods or three physical problems. Okay. Three types of analysis can be done based on the physics of the problem. We actually saw now the length capacitance method. Now we are actually going to see the semi-infinite method. Okay. Semi-infinite method. Okay. So that's what we are actually going to see now. Yeah. First of all, a semi-infinite, it is actually a body which is actually extend to infinity in all but one direction. Okay. A semi-infinite, a semi-infinite solid is idealized body that extends to infinity in all but in all but one direction. Okay. What does that mean is, suppose if you are having any body like this, okay, if you are having any body like this, so here what we are actually saying is, uh, so we are actually saying this is x, y, and z direction. Okay, so it is actually extending to infinity in x direction. Okay, minus x minus infinity and plus infinity in y direction. It is actually extending to infinity and minus infinity in z direction, and in x direction also it is extending to infinity only on one side. Okay, but we are having x is equal to 0 plane. Okay, so it is actually extending to infinity in all but one direction. In one direction, in the x direction, it is actually extending to infinity in only one direction. Okay, it is not extending to infinity. It is not extending to infinity in the minus x direction. Okay, so such kind of a body is actually known as a semi-infinite solid. Okay, it is actually in the x direction. It is actually having only kind of a semi-infinite only. Is not fully infinite. But in y and z direction, it is actually going to be fully infinite. Okay, so that is actually semi-infinite method or semi-infinite body. So we will actually first do the analysis. But when we are actually going for some applications, or when we are actually going for a finite body, which is actually the practical bodies, there also we can actually see that this semi-infinite method can be actually used. Okay, so that's why the semi-infinite method is actually going to be important. Even though we are actually saying it is actually an idealized body, it is actually of very high practical importance, especially when we are actually talking about transient temperature methods using liquid crystal method and all. So this semi-infinite method is what we are actually using. Okay, so this is actually of very importance. It is actually of a very high practicality. Okay, and that's why we are actually studying it all here. Okay, so I hope you have actually understood now what is actually the semi-infinite. Now we have to actually see why it is actually going to be important. Okay, and what is actually the speciality for this? In a lambda capacitance, we said that we are actually taking a body as lambda capacitance because uh, we are actually assuming the temperature gradient within the surface to be equal to 0. There is actually no gradient within the body. And what is actually the speciality for this semi-infinite? That's what we are actually going to see. So what happens is that if we are actually going to change the temperature at x is equal to 0 plane, okay, when we are actually going to change the temperature at x is equal to 0 plane, the x is equal to infinity, that is actually unaware of the changes. Okay, so that is actually going to be unaware of the changes. So that's why the semi-infinite solids are actually going to be important. Okay, so what does that actually mean is, if this is actually our semi-infinite body in the x direction, okay, in the x direction, so it is actually extending to infinity. So initially, suppose it is actually at a temperature Ti. Okay, so initially it is at a temperature Ti. We can actually say this is actually some Ti temperature. Okay, suddenly I have increased the temperature to Ts on the surface. On the surface, I have suddenly increased the temperature to Ts. Okay, how do you think the temperature going to be at T is equal to 1? I will actually give three options. It is actually going to be like this. At T is equal to 1, at T is equal to T1, some temperature, some intermediate temperature. So it might be actually like this, or it is like this. So whether it is actually 1 or 2, or is it like this, say 3? How is actually going to be 1, 2, or 3? How do you think the temperature variation with it?
Three.
So three maybe, sir.
Yeah, very good. If it is a lambda capacitance, obviously it is actually going to be first 1. Okay, and at the time t is equal to 0, at the instant we are actually supplying this, it is actually going to be 2. But at any intermediate time, it is actually going to be 3, right? Because at inlet the temperature is actually going to be there, and yeah, at the entry we are actually going to have the temperature Ts, and it actually gradually reduces to temperature Ti. Okay, so that's what happens at any intermediate temperature. So as the time increases, suppose this is actually at the time t1, okay, it is at time t1, and this is actually at time t2, and it might be something like this. Sorry, it will not be linear. Something like this, okay, time t3, and something like this for t4, okay, something like this for t4. So this is actually how time is actually increasing. As the time increases, we can see that near to the surface, the temperature is actually increasing. But we can actually see that, okay, this is where x is equal to infinity. X is equal to infinity is actually over here. Okay, so we can actually see that at x is equal to infinity, so that effect is actually not there. Okay, at x is equal to infinity, it is still Ti only, which is actually the initial temperature. Okay, so that is actually the speciality of this semi-infinite solid. Okay, so in a semi-infinite solid, on the the inner bulk of the fluid or inner bulk of the object is actually unaware of the boundary conditions. Okay, so the inner bulk of the body, from here we can actually say that from here, whatever the body we are actually talking about, it is actually unaware of the boundary conditions. Okay, so that is what it is actually known as the semi-infinite solid. Okay, so we will actually practically see how it is actually going to be useful later, but for now you actually understand that at x is equal to infinity, obviously whatever the time we are actually talking about, okay, whatever the time we are actually talking about, obviously at x is equal to infinity, it is always going to be unaware of the situation, right? So we will actually see later practically what we are actually talking about. But for now, when we are actually talking about semi-infinite, just think that at x is equal to infinity, it is always unaware of the practicals or unaware of the boundary condition. Okay, so that is actually what the semi-infinite solid is all about. Okay. So if you are actually writing it, if the thermal condition, if the thermal condition. So this is actually in x direction, and this is equal to x is equal to 0. Okay. The thermal condition at x is equal to 0 is changed, then location far away from the boundary, far away from the boundary, that is at x tends to infinity, is not affected by the change, is not affected by change boundary condition at x is equal to 0. Okay, so that is actually the semi-infinite solids. So based on this, therefore, we can actually derive our basic governing equation as well as the boundary conditions. So for the so now we are actually assuming our yeah, we are now trying to reduce our governing equations as well as the boundary conditions. So boundary conditions, we are actually saying that uniform, okay, uniform initial temperature, okay, uniform initial temperature, uniform initial temperature. So that means T at any x, at any x, at a time t is equal to 0 is equal to Ti. Okay, so therefore we can actually write over here, provided surface or the surface is, so solid is semi-infinite in x direction, semi-infinite, semi-infinite in x direction, in x direction. Okay, semi-infinite in x direction. Solid is semi-infinite in x direction. We no need to even provide. Solid is semi-infinite in x direction. Okay. So again, since we are actually talking about semi-infinite in x direction, the any variations in y as well as z directions we are actually neglecting, because that is actually negligible compared to the temperature variation in the x direction. Okay. Yeah. So this is actually 1D transient equation. Okay. So it is actually function only, the temperature is actually function only of x as well as the time. Okay. Uh, so this is actually the initial condition now. So now we have to actually see what is actually the boundary conditions. Okay. So at t is equal to 0, we know that the boundary condition change to Ts. Okay. So that means t at x is equal to 0 at any time t is equal to Ts. Okay. T at any at x is equal to 0 at any time t is equal to Ts. Okay. But this is not affected at x is equal to infinity, right? So this is not affected at x tends to infinity. Okay, so that means what we can actually say is t at x tends to infinity at any time t is equal to still t initial only, because the boundary condition is actually not affected by the at x tends to infinity is actually not affected by the boundary condition. Okay, so if we are actually measuring the temperature at x tends to infinity at any time, it is actually going to be initial temperature only. The temperature is actually not at all varying over there. Okay, so these are actually the conditions. Now we can actually formally write this. Okay, so this is 1D steady state equation, 1D unsteady equation, unsteady equation, unsteady equation, obviously without heat generation, without heat generation, without heat generation. Okay, so therefore the equation is going to be dou square t by dou x square plus 1 by alpha, or is equal to 1 by alpha dot t by dot t. Okay, and boundary conditions are t at at any x at time t is equal to 0 is equal to ta. That is actually the initial condition. Okay, t at 0 t is equal to ts. Right. So that is at x is equal to any x and t is equal to 0. And the second one is at x is equal to 0 and t is equal to any time t. So that is actually the boundary condition, first boundary condition. Second one is t infinity t is equal to tl. Okay, so that is x tends to infinity, t is equal to t. Okay, so these are actually the boundary conditions. So we have two conditions, so two boundary conditions and one initial condition. Okay, so with this we can actually solve this. But again, solving it as actually a bit involved. We can actually use a Laplace method, etc. Something you can actually use, but again, this is actually the partial differential equation. Okay, solving partial differential equation is actually very difficult. So what we have to do is we have to actually somehow convert it into an ordinary differential equation. Then only you can actually solve the partial. Okay, so there are actually many methods for doing that. First one is actually a separation of variable method is actually there. Okay, and do you remember any method you actually used in fluid mechanics for flow or flat surface? Do you remember using any method for flow or flat surface in the fluid mechanics? Flow or flat surface, you actually used some technique to convert a partial to a ordinary differential equation. Okay, so in the boundary layer, you actually said that, if you remember, boundary layer, we actually said that the velocity profile is actually going to be changing, right? So velocity profile u is actually going to be a function of x and y. So you said that, okay, it is actually going to be x and y. It is so therefore it is actually partial. So it is actually difficult to solve and all. You said instead of solving for u as a function of x and y, you said you are actually going to solve it as a function of a particular term eta, right? So where you said eta is actually a function of x and y. So but u by u infinity, it is actually function only of eta, right? You actually introduced a new variable. Okay, you actually introduced a new variable which is actually a combination of x and y. Okay, such that now the u is actually function only, or more than u by u infinity now is actually a function only of eta. Okay, so therefore you actually successfully converted u in a PDE, partial differential equation, to u by u infinity into ODE. Okay, so what was that actually that resulting equation? Do you remember? F 2 dash plus 2 f dash plus is equal to 0, something like that. Do you remember? What is that equation called? Do you remember Blasius equation? Do you remember this technique? Do you remember what is this?
Yes, sir. Technique we remember, but yeah, equation
Yeah.
not so
So,
clear.
but what is this technique called? What is this variable called? Eta called? That eta is actually called the similarity variable. Okay, so what does that mean is, if you are actually writing u as an x and y, you actually saw that the velocity profile is actually varying over time. Oh, if you are actually writing a velocity profile at different x's, so you can see that the velocity profiles are actually different. But if you are actually writing u by u infinity, so u by u infinity, okay, as a function of eta, it is actually constant everywhere. Okay, so there is actually no variable because eta is actually function of x and y. Okay, so say velocity profile at 1, 2, and maybe 3. So everywhere you can actually combine it to a single velocity profile. Okay, so now it is actually u by u infinity, and it is actually function of eta. Okay, suppose if you want to find what is actually velocity profile at x is equal to x1, you want the velocity profile at x is equal to x1, you have to actually put it into this particular equation. So because we know that eta is actually function of x and y, okay, and you have to actually put into this the x1, and you can actually vary y, and you will get from this, you can actually find what is actually the velocity profile at u at x1. Okay, and if you want to find what is actually velocity profile at x2, x is equal to x2, from here you will actually get it is actually a bit different from that at x1. So this is actually u is equal to u at x2. Okay, so you are actually getting a single profile. You are getting a single profile. So that means this profile u by u infinity is actually same everywhere. So there is actually no everywhere also. So because x and y you are actually combined into a single variable. So there is actually no variation of x and y separately. If you are actually varying eta, it actually inherently varying x as well as y, right? If you want the velocity profile at a particular x1, you have to put that into the equation, and then you can actually derive what is actually happening at x1. Okay, so everything you are actually getting from a single variable. So that is actually the self similar solutions, because here u by u infinity, if you actually see, that is actually similar everywhere. U by u infinity is actually going to be similar everywhere. So since it is actually similar everywhere, you actually combined at the various locations into a single variable, which is actually eta. Okay, so where eta is actually function of x and y. So that is actually the self-similar solution. A similar technique we can actually use it over here also. Okay, how can we actually use it over here? So here, what are actually the variables in our heat transfer problem? What are actually the variables? Instead of x and y, what are actually the variables we have in our hand now?
X and T, sir.
X and t variable. Okay, so now we are actually trying to see, instead of eta as a function of x and y, whether we can actually have it as a function of x and t. So what I am actually saying is, suppose this is actually a semi-infinite solid. Okay, so we said that this is actually varying with x, and the time ts and ti, we said that it is actually varying with the time, right? So this is actually there. So we said that t1, t2, etc. Okay, for a particular x as well as particular t, we are actually having one value. What I am actually saying is, instead of plotting for at a different along the x, what is actually the temperature variation for a particular t, if we can actually combine these two, if you can actually combine x and y together, so you have to actually plot only a single curve. Okay, if this is actually an eta, okay, we are actually saying at eta, it is actually t is actually a function of eta. That's it. Okay, where eta is actually going to be a function of x and t. Suppose if you want to find what is actually the temperature variation for T1, okay, so you know what is actually the profile for this, you know what is actually this variation. So but eta, as we said, is actually a function of x and time. So into this particular curve, if you are actually putting your t1, you can actually derive this particular variation, okay, at t is equal to t1. And if you are actually putting into t2, then you will actually get this particular variation t2. Okay, so but you don't have to actually find t1 t2 separately, so you are actually finding all together into a single one. Okay, so likewise, if you are actually interested in is, for a particular x, say x is equal to x1, x is equal to x1, x is equal to x1, how it is actually varying with the time. Okay, so how it is actually varying with the time, so that also you can actually find, instead of x, you can actually put x1. Okay, so then you will actually get the plot how it is actually varying with time. So it is actually might be actually varying something like this. Initially, there is actually sudden increase, and then it will be actually slowly rising up. Okay, so that is also possible. But for a particular location, how it is actually varying with time, or for a particular time, how it is actually varying with the time and all. Okay, so all those things you will actually get from this single curve, because there is actually only one variable associated with that. So we are actually comparing x and t into a single variable, because here you can actually see varying with the time, it is actually self similar, right? So only that it is actually stretched scale to some extent. For example, the temperature profile at T is equal to T1 and T is equal to T4, they are actually similar. It is actually scaled up or scaled down. Okay, so that's why we are actually saying that some sense self-similar uh, solution is actually possible. Okay, so self-similar means again we are actually comparing x and t into a single variable, so that we are actually getting a single solution. Okay, so it will be more clear when we are actually seeing the solution later. So there is actually some mathematical methods for finding this uh, solutions and all. Okay, so the single variable, how to find this eta, there are actually some mathematical techniques available. We are not going into detail for that. From physics, some physical analysis also we can actually come up with. Okay, so that's what we are actually going to solve now. So we are actually converting this PDE into an ODE using the cell similarity method or similarity transformation. Okay, so convenient, most convenient method in this condition is transformation. Similarity transformation. Okay. So because we know that for a steady state condition, this temperature was actually a function only of x. So we directly got it in an ODE form. Governing equation was coming directly as the ODE form. In the lumped capacitance also, it was function only of temperature. It was not a function of x. Okay. So there also we actually got it directly in the ODE form. But here in the transient unsteady form, unsteady 1D conduction form, here it is actually a function of x as well as temperature. So it actually automatically comes in the partial differential form. So we need to actually convert it into OD. So that's why all these headaches comes into picture. Okay. So this is actually the self similarity form. So for this x and t need to be combined to a single variable eta. Okay, and equation, so here we can actually call it as 54 equation number. Okay, and 54 reduces to an ODE in eta. Okay, is that clear? Is the similarity solution is actually, or similarity that concept is actually clear for you? It is not. I can repeat. No issues. Is the similarity self-similar condition or that concept clear?
Yes, sir.
Yes, sir.
Yeah, very good. So that's what we are actually going to do now. So now it is all mathematical. So we can actually say we are not going to see how we are actually deriving this eta. We can say using some mathematical techniques. Techniques. So eta can be actually given as x by 2 root alpha t. Okay. So this is actually the self-similar variable. We can actually call that root alpha t as a penetration depth. penetration depth. Just some term we are actually giving. That's it. Okay. So this is actually yeah. So this eta is actually the self-similar variable. So here you can actually see that eta is actually a function of x as well as t. Okay. Yeah. So now we need to actually convert our partial differential equation into ordinary differential equation. Okay. So for that we need to actually find convert all the terms into this in terms of eta. So we need to actually find a dou t by dou x. Okay. So dou t by dou x we can actually write as dt by d eta, because t now is actually a function only of eta. We are actually saying, okay, into dou eta by dou x, okay, is equal to what is actually dou eta by dou x? Dou eta by dou x is 1 by 2 root alpha x. Okay, so 1 by 2 root alpha t into dt by d eta. So in our equation, what we have is dou square t by dou x square. So we need to actually differentiate this whole thing. Okay, is equal to d by d eta of dou t by dou x into dou eta by dou x. Okay. So that we are actually going to get 1 by 4 alpha t square t by d eta square. Okay. Yeah. So again, we need what is actually dou t by dou t is equal to again dt by d eta into dou eta by dou t. What we are actually getting is minus x by 40 root alpha t into dt by d eta. Okay. So now you can actually see that we have actually converted dou square t by dou square in terms of dou square in terms of eta, also dou t by dou t in terms of dou t by dou eta. Okay, yeah. So that's how we are actually converting our ordinary partial into ordinary differential equation using this similarity technique, self-similar technique or similarity transformation. Yeah. So now our equation actually converts to 54 becomes now 54 becomes what? So now we need to actually put all these terms into that. That's it. So here 1 by 4 alpha t d square t by d eta square is equal to uh, 1 by alpha into minus x by 4t root alpha t into dt by d eta. Okay, so that is actually the equation. So here we can actually cancel some terms. 4 cancels, alpha cancels, t cancel. Okay, but now what we are actually getting is d square t by d eta square plus x by root alpha t dt by d eta. Okay, but what is actually x by 2 root alpha t? Eta is equal to x by 2 root alpha t. Okay, so therefore we can actually write x by root alpha t is equal to 2 into eta. So therefore our equation coming to be d square t by d eta square plus 2 eta dt by d eta is equal to 0. Okay. Yeah. So, but in order to solve that, we need to actually have our boundary condition also in terms of eta. Right? Boundary condition also we need to actually make up in terms of eta. So, therefore, we need to actually write T0T, because that is actually the initial condition. Okay. No, initial condition is Tx at any time t is equal to Ti. So that was actually our initial condition. Okay, so how can we actually write that? Okay, at t is equal to 0 means here eta tends to t is equal to 0 means eta tends to infinity.
Infinity.
Yeah, very good. So therefore we can actually write, we can actually give this as t of eta tends to infinity. Okay, so any other terms coming? Only one time, right? So here we are actually saying x comma 0 because there were actually two terms. So here we are having only one term. So therefore t at eta tends to infinity is equal to ti, and the boundary condition at t x is equal to 0 at any time t is equal to ts. How can we actually write that? At 0, so x becomes 0, t at any t. So eta is equal to going to be equal to 0. Okay, so this one given us eta is equal to 0, it is equal to ts. Okay, so actually in order to solve this boundary condition, how many in order to solve this particular equation, how many boundary conditions required? How many boundary conditions required?
Two.
Two, sir.
Yeah, very good. So, but if you remember our basic equation, it is having three boundary conditions, right? So there is actually one initial condition is actually there, as well as two boundary conditions are actually there. We cannot actually neglect this also, even though we have actually converted our equations, we cannot actually change our physics. Okay, so we need to actually see what is actually happens to our third boundary condition also. Okay, so that actually says at x tends to infinity, t is equal to ti. Okay, how can we actually convert that? Okay, so we are actually saying x tends to infinity at any t. Okay, so that actually converts to eta tends to infinity. Right? We are actually saying x tends to infinity. So therefore, we can actually see that this third condition also gives us the first boundary condition over here. Okay, so that is actually another criteria which we need to actually see. So it will automatically come. You think we actually said using some mathematical techniques, we actually put it like this, right? So if you are actually doing a good job, then you can actually see that our three boundary conditions have actually now converted to two boundary conditions. Okay, three conditions which was actually initially there, it is now converted to two boundary conditions. Okay, because in order to solve this, we should be having two conditions only. So if we are having a three condition, then that is actually an extra condition, and our constraints are actually going to be higher. We cannot actually solve the equation. Okay? So therefore, we should be having only two conditions, and you can actually see that two conditions which were actually there in the PDA now combined, and it is actually giving the same condition. Okay? So now we are having a equation, okay? Equation 55, a ordinary differential equation, a second order ordinary differential equation with two boundary conditions. Okay? So it is actually easy for us to solve now. Since it is actually not that easy, I would actually say it is actually not that easy, because this is actually this non-linearity is actually comes into picture, because here eta is actually coming over here. Okay, so therefore it is actually not that easy, but the solutions is actually given in the textbooks. So what we are actually saying is we are just going to see the answer solution directly. Okay.
But sir, how did we get that expression eta equal to that x by 2 root alpha t?
Yeah, that's what. There is actually some mathematical techniques are there. Okay.
Okay, sir.
Yeah, so some mathematical techniques, because you need to actually first consider a variable eta, okay, and then you have to actually multiply your equation, basic equation, with that, and you have to actually reduce it. It is actually a lengthy mathematical technique.
Okay, sir.
Okay, yeah, from from just directly from your uh, what we can actually say, directly from the physics also you can actually have that, but you will not actually get the right tip. Okay, so just showing you, okay, what you can actually say is you can actually say that eta is actually a function of x by delta. Okay, so delta you are actually saying x is delta is actually a function of time. Okay, so that's what you can actually say. So, but then you have to actually find what is actually delta. So what you
Yes,
can
sir.
actually say is dou t by dou t is equal to alpha into dou square t by dou x square, right? Okay. So, but we don't know what is actually delta. You are just saying that eta is actually x by delta, and you are actually saying delta is actually a function of time. We don't know what is actually delta. I'm actually trying giving you a method, just a dimension analysis to see how we can actually derive that instead of going the full mathematical. So this is actually our basic equation, right? So now what we are actually saying is, just if you are actually analyzing the mathematical or just a uh, dimension analysis, if you are actually doing, t is actually varying from ts to ti, right? Over a time t for any particular location we are actually seeing. Okay, so that is actually the variation you can actually have, is equal to alpha times here also. T is actually temperature is actually varying from ts to ti. Here x square is actually coming. So here instead of x, we are actually writing the some length x. Okay. So if you are actually doing that, then you can actually see that delta is actually going to be equal to alpha into t. Okay. So that's how you can actually write. But here again, that two term is actually not coming into picture. So we cannot actually say equal to sign over here. What you can actually say is that similar. Since we are just
That
doing
will
some
give empirical formula
yeah, some
only.
empirical, some method we are actually
Relation will get, yeah.
just getting a feeling of what is actually delta.
Okay, sir.
Okay, yeah. So that is how you can actually say. What I'm actually saying is, if uh, yeah, so we are actually saying is at any delta over here. If you are having any delta like this, okay. So initially it was yeah. With the time, it is actually varying from ti to ts, okay. And x actually varies from ti to ts again. Over here, it is actually ts, right? So likewise, some dimension analysis, if you are actually doing that, then you will get an idea that delta is equal to alpha into t. Okay. But again, that two term is actually missing over here. So therefore, we can actually say it is not equal to, it is actually similar to alpha t. Okay. But with the proper mathematical techniques, you can actually directly get its deltas 2 into alpha t, 2 root alpha t. Okay, so this is actually how we can actually get the feel for this. Okay. Uh, yeah. So that's how we are actually getting these solutions, or that's how you are getting this PD to ODE, and that's how you are actually converting your boundary conditions into the new variables. Yeah. So now you can actually solve this solution to here you can actually write. So this is 55 or 56. So that eta we have actually, yeah, this is actually 55, right? With 56a is okay, and directly giving the solution t minus ts divided by ti minus ts is equal to 2 by root pi integral 0 to eta e raised to minus eta square d eta. Okay, so this is actually the solution, but luckily for us, this is actually the error function. Okay, so therefore we can actually write as t minus ts divided by ti minus ts is equal to error function of eta. Okay, so this one we can actually give us 57. So error function, we know that for an error function it is actually tabulated values. Okay, for a particular eta, what is actually going to be the error function corresponding to that? Because this is actually the integration. Okay, so this is actually the integration for a particular eta. You need to actually put the eta into here. You have to actually do the integration from 0 to that particular eta. Then you will get a particular value. So that is actually the error function. So error function and then tabulated values, it is actually available for us. Okay, so you have to actually take that and you can actually see them. So let me see whether the error functions are actually available with me. I'm sorry, error functions. I haven't taken that now, so I will actually show it to you in the next class. Okay, so from the textbook. Uh, from the textbook, it is actually available. So it will actually gives you a tabulated value like this. Okay, so tabulated value for a particular eta. Okay, for a particular eta, what is actually the corresponding error function. Okay, for a particular eta, what is actually going to be the corresponding error function? Directly you will actually get. Okay. So now if you actually see T is actually the unknown value. Ts we actually know. Surface temperature is actually the boundary condition. Ti we know. This is actually the initial condition. Again Ts we actually know. Okay. And then for a particular eta value, you will get what is actually the corresponding error function corresponding to that. Okay. So therefore, you can actually draw what is actually going to be T minus Ts divided by Ti minus Ts. Okay. So it is actually going to be something like this. So initially it is actually going to be something like this. Okay. Yeah. So therefore, you can actually have the particular graph on it. Okay. You see the values. Okay. Yeah. So I have actually plotted also. Let me just plot it clearly. Okay. So this graph, it is actually for a. So this is actually for a slab like this. So this is actually for a slab like this. So this is for a slab like this. At x is equal to 0, it is actually having some boundary condition, and towards the center, how it is actually going to be. Okay. So this location, that is actually x is equal to 0, and yeah, so this is actually going to be some infinite. Okay. On the x-axis, it is actually going to be infinite. I don't know whether I can write it. So this location, that is actually x is equal to 0, and this is actually tends to infinity. Okay. So this one, so this is actually the graph for that. So here, how I actually draw this, I actually taken time t is equal to 25 at a particular time. Okay. So this is actually the time t is equal to 25 second. Okay, this time t is equal to 25 second, and I am actually saying, okay, along the length, okay, I have actually taken 5 points like 1 centimeter, 2 centimeter, 3, 4, and 5 centimeters. Okay, so 1 centimeter, 2, 3, 4, and 5 centimeters I have actually taken. Then you can actually see that yeah. So this is actually the yeah. So this is actually the eta. Okay, so this term is actually the eta. So this is actually the eta term. Eta is equal to x divided by 2 square root of alpha into t. Okay, alpha also I have actually taken some value over here. Okay, alpha I have actually taken some value over here, 0.00002. Okay, and time we are having as 25 seconds. Okay, yeah. So therefore, eta is actually calculated as F19. F19 is actually x divided by
2 into square root of alpha into t. Okay, alpha into t. 1 minute. I would actually say C. So that is actually the eta value, and corresponding to that error function in Excel, you will directly get the error functions. Okay, in your exam and all, I will give you the tabulated value of error function. So corresponding to the error function, you can actually have. Okay. So you can actually see that initial temperature Ts. Yeah. So Ts I have actually taken as 100 degree, and initial temperature I have actually taken as 30 degree. Okay. So initial temperature taken as 30 degree and Ts taken as 100 degree, and based on that I can actually calculate what is actually T. Okay. So from our equation we can actually see that T minus Ts divided by Ti minus Ts. So Ts I have taken as 100, Ti I have actually taken as 30. Okay, and is equal to error function. So we said that error function is equal to x by 2 square root t. Okay, and if I am actually fixing my temperature or time as 25, as the x varies, eta varies, and corresponding to eta, error function also varies. Okay, so here we can actually see that t is equal to, so therefore I can actually write t is equal to error function into Ti minus Ts plus Ts, right? So that's what I have actually written over here. Okay. H19, that means error function into Ti minus Ts. Ti minus Ts is equal to minus 70. Okay, plus Ts, that is equal to 100 degrees. Okay. If you actually do that, you will get what is actually the temperature at that location 0.01. Okay, you will get at 0.02 the same equations you can use, only that your eta value will be actually different because you have actually changed the x. Okay, so likewise you can actually see how the eta values are actually going to be different. So yeah, so if you are actually plotting that, then you will actually get the curve like this. Okay, you are actually going to get a curve like this. So that is actually the temperature over here. So what do you think if I actually say time is equal to say 1 second? If I take time t is equal to 1 second, then you can actually see that it is almost equal to the initial temperature. Okay, almost equal to initial temperature, which is equal to 30. Okay. So therefore you can actually see that 30 almost everywhere it is actually 30 degree. So this is what we can actually call it as a semi-infinite solid. Okay, we can see that the solid is actually suppose assume that the solid is actually of thickness 0.05 meter, that means 5 centimeters. Okay, so therefore you can see that even though I change the boundary condition, so boundary condition is that we will actually put x is equal to 0 also over here. We will put 0 also over here. So so you can actually see that at the time t is equal to 0, whether t is equal to 0 also works because it will not actually work because it actually becomes our odd error function. We can actually say 0.01. Okay. Just after that, we can actually see that at the surface it is actually going to be there, but here you can actually see that even for everywhere, we can actually see that the time is actually going to be like this. Okay. So, but if you are actually increasing the 0.001, so here you can actually see that if you are actually increasing the number of terms in between, so then you will get a more better relations. Okay, more better graph. Okay, here it is actually coming down 0 because of the graph. If you are actually putting one point in between, also that graph will not actually come down like this. Okay, so just see the points at least. Okay, so you can actually see that for a time, okay, for time 0.02, okay, 0.01, 0.1, we can actually see that everywhere inside is actually unaware of the boundary change in the boundary condition, right? So therefore, we can actually call this as a semi-infinite solid. So suppose if I am actually increasing to say 1 second, we actually saw that here at 0.1, at 0.01, that means at 1 centimeter, we can see that the temperature is actually increasing. But everywhere else, it is actually unaware of the change in the boundary condition. Still, therefore, we can actually call it as a semi-infinite. So instead of 1, if I'm actually going to make it to 10 or make it to 5 seconds, we can see that till 0.3, 0.03, we can actually feel the temperature is actually varying. But still 0.4 as well as 0.5 or 4 centimeter as well as 5 centimeter, it is still unaware of the change in the temperature. Okay. Now, if I'm actually increasing to say 10 seconds, okay. So now you can actually see that now the temperature even at x is equal to infinity. So in this case, we are actually saying maximum it can go up to 5 centimeter only, right? So here you can actually see that now the maximum possible x is actually now start to feel the boundary conditions. Okay. So therefore, we can actually see that. So for any conditions more than say 7 seconds or something, the full body is actually now feeling the change in the boundary condition. If you're actually putting it as 8, now you can actually see here the temperature is actually going to increase a little bit. Okay, so we can actually see that for any time greater than 7 seconds, even the farthest x available for the body is actually now feeling the change in the temperature. Okay. So therefore, we can actually say that for this particular condition in which the body is actually of a 5 centimeter width, for this change in the boundary conditions, till 7 seconds, it is actually acting like a semi-infinite solid. Okay, till 7 seconds, it is actually acting like a semi-infinite solid. But if you are actually saying, okay, my body is actually instead of 5 centimeter, it is actually of 10 centimeter. Okay, if it is actually of 10 centimeter, here still you can actually see that even at 7 seconds, at the 10 centimeter, at the farthest end, it is still at 30 degrees. Okay, so suppose I am actually increasing to say 15. Okay, still it is actually not feeling any change. Okay, still it is actually not feeling any change. So in this case, if I am actually increasing the body to again the length of the body I am actually increasing, then it is actually acting as a semi-infinite for a longer time. Okay, so that is actually a very crux for this. So initially, even though we are actually talking about a body which is actually finite in thickness, for a very small time, it is still acting as a semi-infinite solid. So that is actually the importance for this. Okay, so that we will actually see in a much clear sense when we are actually talking about the finite bodies. Okay, yeah. So So that's how you can actually appreciate this. So with a only a function of error function, or it is just as a function of eta and t, or it is t is actually now function only of eta. Okay, and therefore we can actually get us only one single curve. Okay, and with that single curve, we can actually find what is actually going to be the temperature variation, or we can actually see what is actually the variation at any particular x or with any particular time also. So whatever we actually saw now is for a particular time. Okay, say for 10 seconds. For 10 second, how the temperature variation is. So that's how we actually saw. Okay. Instead of that, you can actually plot again for a particular x, say 0.01. Okay. 0.01, how it is actually varying with the time. So that also you will actually get from the same meter. Only that the tabulation will be actually going to be a bit different. Okay. So that is actually the beauty for this cell similar equations. Okay. So if you want to plot me as so here, if you want to plot me as a theta, a t by t infinity as function of that itself, then it will be only the error function, right? Yeah. Yeah. Let's see. So this is actually the only curve, means for the curve for this one. Okay, for the curve for this one, it is actually not like this. Okay, so yeah, it is actually the other way around. Actually. It is going to be the other way around. As x is equal to as the eta increases, the error function of eta is actually increasing. That means this value, this term, this particular term, that is actually being plotted over here. T minus Ts, this is actually the term. On x-axis, it is T minus Ts divided by Ti minus Ts. On y-axis, that is actually the eta. Okay, so that is actually the single curve. So that is actually defining. That is actually the single curve that actually defines the variation of temperature with respect to x as well as with respect to time. Okay. From this curve, for this curve, whatever, yeah, from this particular curve, we are actually coming up with this curve. Okay. From this curve, which actually depicts eta versus t minus ts divided by ti minus ts. Okay. From that particular that common curve, we can actually come up with for a particular time how it is actually varying along the x, or a particular x how it is actually varying with respect to time. All those things we can actually come up with. Okay. Everything based on this single curve. Okay. So that's why we are actually calling it as a similarity transformation. Okay. So t is actually going to be a function only of eta. From that single curve, we can actually come up with any time variation along the x for any x variation with respect to time, anything we can actually plot. Okay, is that clear? Is it clear? It is not clear.
Yes, sir.
It is not clear.
Yes,
Anyone
sir.
having any doubts, please ask. I can actually repeat it again. No issues. Okay. Yeah, so you can also just plot these curves etc by yourself, so that actually gives us a better idea. Okay, so that actually gives us a very good idea of how the equation works on it. Okay, so that's how you can actually find the, or that's how you can actually convert your error function into x and y itself, x and t itself. Okay, so how it is actually varying with the time for a particular x, or how it is actually varying with x for a particular time, etc. So those things we can actually directly get from this particular equation. Okay, yeah. So, and that is actually the importance of semi-infinite solid also. Even though we actually started by saying that it is actually a idealized one, so we have actually seen that even for a very small slabs like 5 centimeter slabs with the given boundary condition till to almost 7 seconds, we can actually consider it as a semi-infinite solid. Okay. So that's what we will actually see in the next section. Okay. Yeah. One more small topic actually left in this, which is actually the total heat transfer. Okay. So now what we actually saw is actually the temperature profile within the surface. Okay. So we actually saw how the temperature profile varying with the time under. Okay. But what is actually again important is actually the heat transfer from the surface, okay, till to a particular time. Uh, yeah. So the heat flux we actually know that Q is equal to minus K
dou t by dou x is equal to 0. Okay, at x is equal to 0. So you can actually see that for a particular time, U surface is actually given as a into ts minus ti divided by root of uh, pi alpha t, pi alpha t. So that is actually the heat flux. Okay, so we can actually say surface heat flux at any particular time. Okay, we can see that at very low temperatures, at very low time, we can see that the heat fluxes are actually higher because yeah. So because we know that at a very low time, at very low time, say time is equal to 1 second, we can see that dt by dx is actually very huge. Okay, so dt by dx is actually huge, so therefore heat fluxes are actually going to be higher. As the time increases, say 5 seconds, so dt by dx at the surface is actually going to be decreasing. So therefore the heat flux is actually going to be decreasing with time. So that's why we can see that there is actually denominator comes in that. Okay, so we can actually call it as 57 K. Okay, so that is actually how we can actually calculate the heat flux at the surface also, which is actually varying with the time. Okay, yeah. So that is actually the semi-infinite approximation. Okay, I hope you actually understood that. And again, remember that what we actually talked about is actually the constant temperature condition. Okay. The constant temperature condition is what we have actually seen. When the temperature is actually suddenly changed, how the semi-infinite solid is actually going to behave. Okay. And also, we are actually going to have the constant heat flux condition. We can actually have constant convective surface boundary condition. Also, we can actually have. Okay. So we are actually not going to derive that, but the methodology is actually going to be same. You can actually go with the uh, boundary condition. You can actually go with the uh, a similar self-similarity solution because the temperature profile within are actually going to be self-similar. It doesn't matter what are the boundary conditions. Okay. So therefore, it is actually going to be different. But the self-similarity technique you can actually use. But since the boundary conditions are actually going to be different, the solutions are obviously going to be different. Okay, so we are just going to see one condition, which is actually the convective boundary condition. So with convective boundary condition, convective boundary condition for semi-infinite solid, semi-infinite solid. Okay. We can actually write as T minus Ti divided by T infinity minus Ti. Okay. So here we can actually write as this is actually initially at t is equal to 0, t is equal to Ti, okay. And the boundary conditions varies to h and t infinity. Okay. So for t greater than 0, minus k dt by dx at x is equal to 0 is equal to h into t infinity minus ts. Okay, so that is actually the boundary condition at x is equal to 0. Okay. So heat transfer coefficient and temperature of the fluid. That's what we have actually known. So therefore here we are actually normalizing as t minus ti divided by t infinity minus ti. So initially what we actually wrote is t minus ts divided by ti minus ts. Okay. You have to be very careful on those steps. So here you can actually write t minus ti divided by t infinity minus ti is equal to uh, complementary error function of eta. Okay, complementary error function. It is not error function. It is actually the complementary error function, which is equal to 1 minus error function. Okay, minus exponential of hx by k plus h square alpha t by k square. Okay, uh, into into again error complementary error function of eta plus h into alpha t by k. Okay. So this is actually the equation we can actually have. So all the terms, so eta is equal to x by 2 alpha t. Eta is equal to x by 2 alpha t. So that's what it is actually coming. And we know what is actually h, okay, for a particular time. If we are actually saying say 10 second, we have to keep the t is actually constant. Okay, so t is actually constant as 10 second, and only unknown is actually now, or you can actually vary x. Okay, we can actually vary x. So all the terms are actually known, so you can actually calculate what is actually coming up, and then ti we know, t infinity we know, again ti we know. So only unknown is actually the t. So based on this equation, you can actually calculate the variation of t for a particular time with respect to x. How the t is actually vary, you can calculate, or you can actually fix the x. You can actually vary the time, and also you can actually calculate how the t is actually vary. Okay. So the same methodology, only that the equation is actually going to be different. Okay. Yeah. Again, with the constant heat flux also, one other equation is actually going to be there. I'm not going to give it out here. You can actually refer the textbook. You can actually find it. Okay. Yeah. So that is actually the method of semi-infinite approximation or semi-infinite transfer, semi-infinite methodology. Okay. So if you have any doubts, we can discuss. Otherwise, we can stop the discussion. Okay. Anything else? Anything to discuss? Okay. Okay then. We'll be having our minor one tomorrow afternoon or in the evening probably after your classes. So maybe we can actually arrange from 4:30. It is just for 15 minutes. From 4:30 we can arrange, or 5 o'clock we can arrange according to your convenience. Okay, we will fix the time, and it will be objective only. The number of questions, etc., will let you later. Let you know later. Maybe max 20 to 25 questions might be actually there, or 20 to 30 questions might be actually there. Okay. And accordingly, time will be actually fixed. And the portion will be actually till fits, including fits. Okay. Yeah.
Yes, sir.
Yeah. So if you have any doubts in any of the portions we thought, you can actually discuss. Okay. You can actually mail me, or you can actually call me, and we can actually discuss. Okay. Yeah. Okay. Okay then. Have a nice day to all.